Good morning, everyone. My name is Artem Bilik. I'm a PhD student in Laboratoire de Mécanique de Normandie in France, and today I'm going to present you our methodological developments for multi-objective optimization with uncertain parameters. First of all, let's define some vocabulary. Here you can see a multi-objective optimization problem with uncertainties definition, where we have a set of performance functions we want to minimize that depends on design variables, which is something we control, and design environmental parameters, or DEPs, which are our random variables that we don't control. And in this problem formulation, one must solve the constraints with respect to the probability of the violation of a given constraint. Our idea is to simplify this problem and solve it as a set of multi-objective optimizations, so that we can get rid of this notion of probability in the constraints. During this presentation, I'll be using Binet-Korn test function as an example in order to explain our methodology. We modified this classical test function by adding some uncertain parameters with a xi vector, which we sampled using known probability density distribution of each random variable. And here you can see an example of three efficient sets for 3 data points, as well as 3 respective Pareto fronts. Our methodology is kind of similar to a Monte Carlo approach, where we sample some parameters and then the function is evaluated for each sampled data point. Then we are going to be interested in the statistics of Pareto fronts that we obtain in this manner. So first of all, mean Pareto front, it is usually not a real existing object, even though it might maybe depend on definition. So we prefer to work with median Pareto front, which is a real existing Pareto. And in order to obtain the median Pareto, we're gonna use some statistics of object developments, and as a metric of distance, it will use a Hausdorff distance, which is defined as a maximum distance between all the minimum distances between two objects. And then we will be interested in some percentiles for the further analysis. To use some classical multi-objective solvers like NSGR2 and make our methodology non-intrusive in order to easily implement it to some commercial software. As I said previously, we start from initial DEP sampling set where we create our random vector xi. Then for each point in this data set, we perform a multi-objective optimization. We get our Pareto front. And then when we have all the solutions, we perform a statistics. We were somewhat motivated to enhance the classical NSGR2 solution. Our motivation could be clearly seen on this figure, where we could compare the reference Pareto front and the Pareto front obtained with direct method. So clearly we don't get the real extremities of the Pareto, and the front does not converge enough, at least for a few generations, as what have been done here. We were also motivated to calibrate a representation model in order to also get a better precision of the Hausdorff matrix, Hausdorff distance, and in order to have an opportunity to calibrate a representation model and to get an access to smaller percentiles later. I'll discuss the implementation strategy, then our parameterization methodology, the statistics of parameter fronts, and we'll finish with an application on a real mechanical problem and the perspectives of our method. Let's now discuss our implementation strategy. We start from DEP sampling, which you can see just here. It is a full factorial DOE that corresponds to a uniform distribution of both random variables. Then for each data point, for each blue point, we perform a multi-objective optimization to find a corresponding Pareto front. So our enhanced methodology is the next one. We start from the mono-objective optimization for each performance function in order to capture the extremities of the two extremities of the Pareto front. In order to converge quickly, we start from we are using the Pincus formula in order to get an initial point approximation. Then all of this data that was calculated is used to create a meta model. A multi-objective optimization is performed on this meta model in order to get the first approximative Pareto front, which will be used as an initial solution for multi-objective optimization. And this gives us an opportunity to obtain converged and nice 25 Pareto fronts, as you can see on the figure here. The main part of this methodology is the parameterization, where we wanted to create a representation model from a truncated polynomial basis for performance function and for DEVs, for design variables. This could be written in matrix form as follows, and then formulated as an optimization problem where we want to minimize the least square distance between our model and the real obtained values from the multi-objective solution. We have two boundary conditions where we fixed the limits of our parameter psi between 0 and 1, and these extremities correspond to the minimums of the performance function. There are some other constraints that are needed in order to get something that corresponds to the wanted Pareto. Here you can see an example of such a parameterization, where on the first figure you can see each performance function and each variable calibration as a function of parameter psi, and the second one is the corresponding Pareto, where we have a good precision of the parameterization. By applying our methodology, we found 25 Pareto fronts, and then we parameterized them, and now we are interested in statistics. And as the measurement of distance metrics, we will be using Hausdorff distance, and in practice we will be obliged to discretize these Pareto fronts in order to get a set of points to evaluate the distance between two objects. And you might ask, why don't we use the rough data set of data points that was outputted from NSGR2 solver? And the answer is very clear. There are multiple advantages, as for example, the first one is that we can adjust the number of points for the Pareto depending on the density and wanted precision. And we can even achieve a true uniformity between the Pareto fronts, that is equidistant spacing, so perfect crowding distance between the points. And this equidistant spacing gives us an opportunity to propose a mean definition, which, so if every Pareto is defined as a set of points, then we can say that the mean Pareto consists of the same number of points, where every point is the mean midpoint of every point. Let's now apply our methodology to a mechanical problem, which is here a steel mounting bracket with a hole fixed on one side and with linearly distributed force on the other extremity. By solving this mechanical problem in static solver, we obtain some displacement field. And our optimization problem is the next one. We want to minimize the mass in order to decrease costs, and we want to minimize the maximum displacement magnitude. We have three geometric parameters that we control, and our random variables are the plate thickness and the Young modulus. We also consider a dependency of the density of the steel that depends on the Young modulus in order to achieve the more clear difference between Pareto fronts and to see more clearly the impact of the changes. As usual, we start from DOE sampling. Here we chose our orthogonal Latin hypercube DOE technique. And for each data point, we then apply our enhanced multi-objective optimization methodology, which is we start from mono-objective optimization for each performance function. We then use all this data to create a meta model and to solve this multi-objective optimization problem and to obtain the first solution approximation. This approximation is used as an initial guess for multi-objective optimization on a real mechanical problem. We then obtain a Pareto front, which is our solution, and we parameterize it. Here, a polynomial of degree 3 was chosen, as the precision was sufficient, as you can see on this figure. And then we apply this methodology to all 20 data points, and we obtain 20 respective Pareto fronts. Also, you can see on this figure some geometries that corresponds to some of the data points. Then we're interested in the statistics of these fronts, and the median was found to be at 3 millimeters for the thickness, which corresponds to the mean value, and the Young modulus was quite far from the mean value, and we'll explain with this by the fact that thickness has a greater impact on the front Pareto positioning, and actually we can achieve a better precision by some applying some methodologies that we'll explain later in other articles. So on this slide you can see the difference between the Pareto front obtained with directly with NSR2 solver and with our methodology for an equivalent total execution time. And clearly, as I said in the beginning, we don't capture the Pareto extremities, and the Pareto front has a better precision by applying our methodology. The main benefit of our parameterization methodology lies in the perspectives. So we get a set of coefficients that correspond to performance function or to design variables. We have a polynomial of degree 3, so we have 4 coefficient types, and then we calibrate the polynomial chaos representation model in order to establish the link between the coefficient value in each case and the corresponding random variable value. So that's the idea. As you can see here for this first coefficient of magnitude example, we calibrate the hypersurface on thickness and Young modulus, and the same we do for the second design variable as well. Then we can regenerate the new DEP sampling and generate a large set of Paretos at a very low cost. And here you can see an example of 10,000 Paretos. And then we can then we perform statistics that we discussed previously, so mean and median value is found. And but what is more interesting is that we can find a much smaller percentiles, like 99 percentile, 99th percentile of Pareto fronts for the further analysis. It is a very small percentile that wasn't accessible with the previous dataset. And that's all. And thank you for your attention. If you have any further questions, please feel free to contact me. Have a nice day.